Season 1, Episode 4, Understanding Actuators, bringing motion to life. Welcome once again to the Robot series. In the previous episode, we explored sensors, the components that allow robots to sense and understand their environment. Today, we are moving deeper into the physical side of robotics to understand actuators, the true muscles of every robotic system. Actuators are devices that convert electrical energy into mechanical motion. They make things move, lift, push, pull, or rotate. While sensors tell a robot what's happening around it, actuators make it act. Every robotic motion, from the spinning of wheels to the gripping of a robotic hand, happens because of actuators. In this episode, we will explore the most common types of actuators used in robotics, how they work, their technical specifications, voltage ratings, pin connections, and their applications in real-world systems. Let's begin with one of the most common and fundamental actuators, the DC motor. A DC motor converts direct current electricity into continuous rotational motion. Inside the motor, an armature rotates within a magnetic field, producing torque through electromagnetic induction. The direction of rotation depends on the polarity of the voltage applied, meaning that reversing the positive and negative wires makes the motor spin in the opposite direction. Most small DC motors used in educational and robotic applications operate between 3 volts and 12 volts, though industrial types can reach up to 24 volts or more. A standard DC motor has 2 terminals, one for positive voltage, VCC, and the other for ground, GND. You can control its speed using a technique called pulse width modulation, or PWM, where the Arduino sends rapid pulses to vary the amount of power delivered to the motor. DC motors are commonly used in robot cars, fans, and conveyor mechanisms where continuous motion is needed. Next, we have the servo motor, which provides precise control over angular position. A servo motor is made up of a small DC motor, a set of gears, and a built-in feedback system using a potentiometer. This internal feedback mechanism constantly measures the motor's rotation and adjusts its position to match the input signal. Servos usually rotate between 0 and 180 degrees, although continuous rotation servos exist for full circular movement. Most hobby servos operate at 5 volts or 6 volts and have 3 wires, red for VCC, brown or black for ground, and orange or yellow for the signal pin, which connects to a PWM output on a microcontroller such as an Arduino. Servo motors are used in robotic arms, pan and tilt camera systems, drones, and any application where precise angle control is required. Another important actuator is the stepper motor, known for its ability to move in small, accurate steps instead of continuous rotation. The motor contains multiple coils arranged in phases. When these coils are energized in a specific sequence, the rotor moves a fixed distance, typically 1.8 degrees per step. This gives very high positional accuracy. Stepper motors usually operate at 5 to 12 volts and are controlled by driver modules such as the ULN 2003, a 4988, or TB6560. The motor typically has 4, 5, or 6 wires, depending on the type, unipolar or bipolar. Each wire corresponds to a coil phase, and the driver ensures that the correct coils are energized in order to move the motor step by step. Stepper motors are commonly used in 3-dimensional printers, CNC machines, and precision positioning devices because they can rotate to exact angles without requiring feedback sensors. Moving on, we have the solenoid, which is an actuator that produces linear motion rather than rotational motion. A solenoid consists of a coil of wire wound around a movable metal core called a plunger. When current passes through the coil, it generates a magnetic field that pulls the plunger inward, creating a quick push or pull movement. Solenoids typically operate at 12 volts DC and draw a relatively high current, so they are often controlled through transistors or relays rather than directly from a microcontroller pin. They are widely used in automatic door locks, vending machines, and robotic grippers where a simple on and off linear motion is required. Now let's discuss relays, which are also electromagnetic devices but serve a different purpose. A relay acts as a switch that allows a low-power circuit to control a high-power circuit. Inside the relay, a small coil acts as an electromagnet. When current flows through this coil, it pulls a metal arm to open or close a separate electrical contact. Standard relay modules used with Arduino systems operate at 5 volts and can switch loads up to 10 amperes at 250 volts AC. A relay typically has 3 input pins, VCC, ground, and a signal pin that connects to the Arduino. On the output side, it has 3 terminals labeled COM, NO, and NC, meaning common, normally open, and normally closed. Relays are often used in automation systems, home appliances, and automotive circuits where the control system must handle devices operating on higher voltages, beyond electrical actuators. Robotics also employs pneumatic and hydraulic actuators, both of which use fluid power. Pneumatic actuators operate using compressed air. When pressurized air enters a chamber, it moves a piston in or out, producing linear motion. These actuators are known for their speed and reliability and are widely used in industrial robotics, pick-and-place machines, and automated assembly lines. Typical air pressure for pneumatic systems ranges from 60 to 120 pounds per square inch, or psi. The airflow is usually controlled using solenoid valves that determine which side of the piston receives pressure. On the other hand, hydraulic actuators work in a similar way but use oil instead of air. Because oil is incompressible, hydraulic actuators can deliver much greater force and are used in heavy-duty applications such as excavators, robotic arms for lifting, and industrial presses. Hydraulic systems operate at much higher pressures, often between 1,000 and 3,000 psi, but they require pumps, reservoirs, and filters, making them more complex and expensive than pneumatic systems. Another interesting actuator is the linear actuator, which converts rotational motion into straight-line movement. Inside, a motor drives a threaded rod or a lead screw that moves a nut or slider along its length, producing extension and retraction. Linear actuators commonly operate at 12 volts DC and have two terminals, similar to DC motors. Reversing the polarity of the voltage changes the direction of motion. They are found in automated windows, solar tracking systems, adjustable furniture, and agricultural devices where objects need to be moved up and down or in and out with high precision. When designing robotic systems, it is essential to understand not only how these actuators work but also their electrical and control characteristics. For example, actuators that draw high current should always be isolated using driver circuits or relays to protect the microcontroller. Proper power supply management is also critical, since motors and solenoids can cause voltage spikes when switched on or off. Using components such as diodes across motor terminals, known as flyback diodes, helps protect your circuit from back electromotive force. In summary, actuators are the devices that give robots the power to move, grip, lift, or rotate. DC motors are ideal for continuous motion, servo motors provide precise angular control, and stepper motors offer exact positional accuracy. Solenoids generate quick linear movements, relays handle switching between high and low power circuits, and pneumatic or hydraulic actuators deliver large-scale motion for industrial systems. Finally, linear actuators provide controlled straight-line movement for mechanical automation. Understanding the voltages, pin configurations, and control methods of each actuator helps engineers and students design efficient robotic systems that are both powerful and intelligent. That brings us to the end of this episode on understanding actuators. In the next episode, we'll move on to explore microcontrollers, the intelligent brains that connect sensors and actuators together to form a complete robotic system. Thank you for watching the Robot series. Keep experimenting, keep building, and keep learning.